All right, so we're gonna start with just a quick video. I'm not gonna run this all the way through, but just to show you what we're kind of up to here. If I can get rid of the contact us. Manufacturing is particularly exciting right now. In additive, a lot of vendors like to say you get complexity for free. That's not as true on the design side.
One of the common problems for any design engineer in manufacturing industry is to strike this balance between the design freedom and the computational complexity.
Our invention offers a lot of nice advantages right now. There's so many things that designers and engineers cannot create, or it's just too difficult to create with the existing tools. So we're giving them new representations, new methods, new functionality that will allow them to create these new amazing products.
One of such problems is the design, representation and analysis of complex parts. And for example, parts that may have lattices in their structure. Think of Eiffel Tower, that is one example of a lattice structure at a macro scale. So the Eiffel Tower consists of arrangement of beams that are connected to each other in a periodic fashion. In fact, one beam may have several other smaller beams, and in fact that is the case with the Eiffel Tower as well. Now imagine increasing the number of beams from a few thousands to a few trillions and connecting them in many more complex ways. So in terms of lattice microstructures for 3D printed part, that is the level of complexity that we are dealing with.
So previously these designs would take, you could take hours even to load them into your design software. And with our representation, we can do that in seconds. We're bringing that down to kilobytes in size. So it's a ridiculously huge savings in representation size.
We could have gone ahead and designed more complex looking lattices, but...
All right, so that's enough of the video here. You didn't come to see videos, so let me put a presentation up here. All right, so I'm Mark Burhop. I work for Siemens Technology, which is basically the research group of Siemens. So I'm really excited for this group here to be here. Like DfAM was saying, there's so many people that I've been wanting to meet that I finally got to meet. There's so many people I've met the last day. It's just wonderful. It's really cool. Usually I would ask, since we're in New York City, who went out and went to see Times Square or whatever, but this group's a little bit different. So who went home last night and did an interface to ChatGPT for your software? So I had that idea. I thought it was really smart talking about that a month ago, and then I learned yesterday half of you all have integrations for your products already. So I'm a little bit humbled now. I'll have a lot more to work on here. I have to raise my game a little bit. So if you don't know Siemens, if you came in on a train today or leaving on a train today, it was probably pulled by a Siemens engine. If you work in the medical field or you've been in the hospital or visit your doctor, you probably saw Siemens on a lot of the equipment there. If you design products or do simulation, maybe use NX or SimCenter or some of our software there. Those are all different business units within Siemens. I don't work for any of those business units. I work for Siemens Technology, which is basically the research group for Siemens. So this is the other group here. For the United States, we're based in Princeton, New Jersey, so it's a really easy trip there. And what we tend to do is we don't sell anything. The real reason I'm here is really to partner with many of you. We partner a lot with universities, with other folks. We work on problems either for our business units. We work on problems for the government. You'll see some work we did with DARPA here coming up, and many of you actually participate in some of this DARPA work as well. a lot of it, or we'll look on some things that are maybe important across all the business units. So you'll see us talk a lot about the industrial metaverse now. Not my talk today, but with me, again, these are some areas that we work on. I'm more on the, I guess, on the green side here, on the left side, but next generation algorithms, which we'll talk about, digital twin technologies, all these things with generative design, a lot of machine learning. So a lot of our folks are working on, ChatGPT, or a lot of the machine learning type things. We do a lot with materials. So Siemens owns a lot of additive manufacturing machines as well already. So we do a lot with developing our own materials, machine technologies. We use all of them. And we love software and hardware. So we have a lot of neural clusters. We do a lot with GPUs and other things there. So if you're looking for, if you're a researcher, want to partner with us, that's great. If you're a PhD student, please come talk to us. We have lots of openings there. So this is the reinventing the wheel. So this is a concept that we had a few years ago, basically in talking to NASA on the spring tire that they're building. And this really came about from a few years ago, 2006. 2016. DARP, those of you that are in your 30s and 40s remember the biggest debate in CAD back then was whether you want a history tree or not in your CAD system. It was kind of settled down, it was kind of not really interesting, and then additive manufacturing comes around and gets a little more serious, and all of a sudden you could create all these wonderful things that you couldn't design. And so that really made things interesting. So DARPA, which is very forward-thinking, said, hey, maybe we need to fund industry to advance the state of the art in design software. How can you now design these super complex parts that you can't design today? And of course, lattices, metamaterials, all these things kind of come into play there. All of a sudden, you're not filling your parts with a or a homogeneous material. It could be anything, right? It could be different materials. It could be all these different shapes and so on. So we partnered, in this case, we partnered with Palo Alto Research Corporation, Georgia Tech University, Michigan State University, and we came up with some new ideas on how to, it was really three things. I'm only going to talk about one today. It was how do you represent these really ultra complex products? How do you do simulation now? So you got this awesome complex thing. How can you do a simulation there? You can't just put a tet mesh on it. And how can you then manufacture these ultra complex parts? So I have parts now that, if I slice them, well, first I can't slice them because they're too big or too complicated. And then I can't send it to the machine because the machine doesn't have enough memory for all the G code that goes there. So there's still, it's gotten a lot better since then. A lot of these DARPA folks were PhD students. They've gone out into industry. They work at a lot of the companies. Some of you may have even worked on some of this. So it's really kind of interesting. So I'm focused on geometry representation. So the additive manufacturing people are my best friends right now because they've created so many really interesting problems. So this blue side here, don't look too closely. I just threw some words up here on things that were, that I remember. But this blue side here was pretty well understood for a while. The new things here that that's going on are really a lot of fun. So these lattices that we're doing, 3MF is changing like crazy. We're talking about metamaterials now. We're doing things with fields and applying fields. We got implicits, so new mathematics. Voxels are suddenly, really in vogue right now, much more than just Minecraft. Topology optimization, so structural is there. CFD is crazy. I put G code down here. I want to fix G code. G code is my, after we kill STL, I'm going to kill G code. But it's still growing strong. And I put code off here in a second. This is what we'll talk about. It's a fun area right now because we still have a lot of things that we can't. There's a lot of things you could probably print right now if you sit there with the G code and write. It's a really fun area to be working on. This is actually an old slide, but it's this was our justification for a lot of the work we did. And now it's more of a state of the industry type slide. Shoes, people are doing shoes all over the place. Consumer products, lightweighting is a big deal. Energy absorption for sports equipment is big. Woven materials, I think we can still do some more things there, but you're starting to see again where we're running filaments or fibers through 3D prints as well, medical devices and so on. So really a lot of interesting things going on where this type of research is important. So if you follow me on LinkedIn, I put this post out here, so don't answer the question. But for the rest of you, here's a really simple box, and it's got film lines going through, cylindrical wires going left and right, up and down, forward and backwards. How much space would that take to represent in whatever format you like? Any guesses? Well, it's huge. If you go back to your dad's CAD system, which was only 6 years ago, if you try to do this with B-reps, solid models, it's huge. It's over a gigabyte. And actually, I got kind of tired of waiting for it. I knew I had a smaller model that was over a gigabyte, so I know it's over a gigabyte. But it's a lot of space, and it's really, this is why you see a lot of people looking up new ways to do things. STL, 237, so it's a faceted model, a little bit smaller, and then these dials on the side, those kind of represent accuracy. So your B-rep is pretty accurate, but the STL, right, to get it that small, you lose a few things. Hybrid CAD, and hybrid CAD, I don't want to call it hybrid CAD anymore because it's really kind of today's CAD. And most CAD systems are not looking at B-reps as their only representation. Most of them are looking at, facet models. They look at graphs. They look at a lot of other things. And in many places, they're becoming equal peers. So you have to work with multiple representation forms as equal peers. You have to be able to take, facet model with the B-rep model and do a Boolean and subtract things and have faces that are meshes and other faces that are precise geometry and maybe other faces that are some implicit definition. So it's really, you see CAD moving that direction a lot. 3MF is awesome. So DfAM, thank you very much. This is using the lattice extension there. So what this does in 3MF is lets me represent lattices as a graph rather than as a faceted model. And it brings it down a huge amount. And then we have, get text messages. We have our representation here, which is representing this by a program, which is tiny, tiny, tiny. And it doesn't apply to everything, but I'll show you some really interesting things here. And really, one of the things I want to do is get you all thinking about this too, because I know there's some really smart people in this room. Apparently, a lot smarter than me, because I hadn't integrated ChatGPT in my software yet. But think about some of this here. If anyone can pronounce this guy's name, that would be great. Kolmogorov complexity. I love what it is. I've never mastered saying it yet. This is kind of the concept here to a certain extent. If you have this, I guess I don't have the laser point. We'll get ahead. If you have a string of characters here, so here A B A B A B A B, and another one just kind of random characters. They're both the same length. The idea is, what's the smallest program you could write to reproduce that string of characters, at least in this case. And the easiest one is you simply write a function that returns that string, right? But if there's some pattern, some information there that you can use, you can really take advantage of it by writing a function that, in this case, it's AB. And so if you're doing random things in your additive machine, this may not work so well, but most of you are not. Most of you have some lattices especially are very much patterning. It's patterning and maybe morphing, which is it's almost the same thing as what we're doing here. We pattern and we morph. So really, let's apply this not so much to compressing data, but let's talk about how we can represent geometry. So this is, one of our examples, and this is actually, I probably took this about 4 or 5 years ago now. This is a 3D print that we did. It's a woven lattice. And the entire representation here is on the screen. So if you take a picture of that and you ran it in our software, it would reproduce this piece of geometry. Compare that to an STL file. If I was to print the STL file, it would be a big box of paper here. It's not really good. If I did a graph of this, it would still be pretty big. So this is really pretty cool. So I may be new with ChatGPT, but I have DALL-E down pretty good. One of the problems, I had a DALL-E said, okay, show me the difference between DNA and elephants. And this is kind of something I got. So this program representation is a lot like DNA, right? The DNA is the program for how to build an elephant. The problem is, lots of there's lots of ways, lots of people written code to generate geometry, right? There's even CAD systems out there that all they do is you write a script and it outputs geometry at the end. That's not the solution. Yeah, you get a small representation, but at the end of the day, after you run the program, you still got this giant representation of things. So you still got an elephant that you need to somehow work with. And so that's not, by itself, is not the solution. We need to think about how we can, not, instantiate an elephant every time we want to do something with it. So this is where it got a little more interesting. We spent a lot more time on the mathematics. There's a lot of papers out there, so I'm giving you the high points here. But go look at the papers if you're really interested. If you do a CAD system. It doesn't matter what CAD system it is, what design system it is. You end up doing queries, and maybe it's not called queries, but it's essentially queries. You say, okay, I got a point at XYZ location. Is it inside, outside, or on the surface of my geometry? And if it's outside, what's the distance from it, from the geometry? Other questions, 3D printing. I want a 2D cross section of my geometry because I'm gonna print layers, right? So give me the 2D cross section of my geometry. Or, what's the weight of my part? How much? What's the mass for NASA? What's the mass instead of the weight? Traditional methods, again, we talked about it. It could take hours. There's one part here that we have, which is one of the DARPA challenges we had, and it's kind of an optimized lattice. You can see kind of the fields running through it a little bit. So I created that, and then I wrote some code to bring it into our CAD system to load it, and it takes hours. It's just so huge and big. And you can easily imagine gigabytes and terabytes of memory for really big parts, especially as these lattices get really small or if you get really big structures. The graphics get slow, so I know a lot of you are struggling with that too. I got so much data, and you need to find ways to bring the graphics down to something that's manageable so the user's not sitting there with the screen jerking once a second as you try to rotate. But after you get everything loaded, it's pretty fast, assuming you can load everything. What we did here was really an idea of kind of a lazy and local method. So we have seconds to load a file. So this big thing is a few seconds. It's kilobytes of memory needed, which some of that you saw earlier. It's fast graphics, regardless of the size. And there's a little penalty though. We have slightly slower queries. And the reason that is because we don't do it in a kind of a lazy and local way. So lazy means I need some geometry I want to see, so we'll instantiate the geometry then. But computers are getting so fast, it works pretty well. We also do it locally. So if you want to look at a slice of your part, we just need to instantiate enough of the geometry around that slice to do the slice. We don't need the whole darn part loaded into memory to do that. Now eventually we will. But it just works really well. And then the other part, some things you maybe need the whole model, right? You wanted to figure out what the mass is of the part. You can't do that, just with local things. But it turns out you can't, because you can now distribute it across all these computers, and each computer, each CPU, or each GPU is calculated a different piece of the model. So we have some scalability now that we can get the mass relatively quickly by parallelizing a lot of these things. And parallelizing has been a challenge. A lot of you know in geometry, it's relatively easy to parallelize your FEA solvers or your renderers or other things like that. But parallelizing around geometry is a harder thing to do. But this is at least one way that we've been able to do it. So again, it's really geometry represented code, and this is one of our examples here. I backed up. So the nice thing here is this part is pretty complicated, but it's kind of at the limit of, say, B-reps if you want to do something like that. You can pick some other methods that go a little bit farther. We got to, you saw the video yesterday, powers of 10. I was watching it hoping it would get to 10 to the 15th, but it got to like 10 to the 5th. We got to 10 to the 15th number of elements in there, which is an astronomical number so that would be 10 to the 15 beams, let's say 10 beams per unit cell, so we get 10 to the 14th unit cells. So if anyone can beat that, you know, I would like to follow you and learn how you did it, because it's just amazing in being able to do something like that. So it's nice too, because the additive guys kept, you know, hey, you can't hold our geometry. Well, now I got this. And say, can you do? It's like, well, you can't do the resolution I need, because I have a lot more detail now on the design side. So I'm ahead of them, at least on this area here. I can kid my additive friends a little bit more. So it's real simple. This is a simple example. I put this here just to kind of give you a flavor for the idea. It's kind of trivial how it works, because I think this is just like kind of a translation model, so you're just patterning with exact patterns. That's a really easy one. But we can do rotation, scaling, all these other things too that make it a little more interesting. But if we have this idea of a kernel. It's kind of like a unit cell, but not quite a unit cell. It's a little bit different, but what you have is some nodes in your kernel, and you define connections. And so you say, oh, this node in N1 connects to N1 in the next unit cell, if you will. We'll stick to that term. In the I direction, and this one connects to N1 in the J direction. This one connects to N1 in the K direction. So that's what you see here. So you have a node here at this spot here, and it connects to here, here, and here. And then you can start to add other transformations. So here it is with, you know, we're showing a range in directions in this little model here. So here we have two directions, or two in that direction, 3. And if you add more and more and more, you kind of see it scales out. So that's kind of the basics of it. And that's pretty easy to understand, right? Lots of CAD systems do patterning and other things like that. But it gives us a nice, easy representation. We can do more things that are a little more interesting. So you saw at the beginning, we talked about the Eiffel Tower in the video. So doing lattices of lattices is really kind of cool, or lattices of lattices of lattices. Where the lattice beams are actually made up of more lattices. You know, that's really kind of pushing the boundaries right now. But again, concise representation. You know, you go to any additive manufacturing conference right now, and you see this table will have a bunch of lattices to show that they can print lattices, and this table will have a bunch of gyroids to show they can print gyroids. So here are gyroids made of lattices. You know, we can do some really interesting things here. You know, some of these things. We could probably do gyroids made of lattices, made of gyroids, if we really wanted to. In a lot of this, you know, I'm talking about lattices. It's the piece we kind of push through in really beam lattices. But this works with other things too. We did some rockets that we were designing with this, representing code, and the ultimate output was voxels, but the rocket itself, the definition was a piece of code that did everything. And so, like I said, it's not just lattices. it's any kind of repeating geometry. Maybe it's not even connected. So here's some Lego pieces that's really a bunch of interconnected parts. This one's fun for my grandkids. How am I doing on time? Does that mean I have plenty of time? I get 0. Oh, I didn't see you. I didn't see. Okay, so I'm going to wrap it up. This is the last slide. I'm sorry. Okay, good and bad. So last thoughts. Program representing with what you want, encapsulating equations is great. Implicits, you can encapsulate implicits in a program really easily. You can encapsulate, voxels in there. You can get derivatives if you want to do some more advanced things. You can encapsulate G-code. This is a good one. So if you have an Ultimaker 3 or above, there's actually a really nice Linux machine inside that you don't know that's in there. So we hacked the Linux machine, and now our Ultimaker 3 takes a piece of Python code, and it runs it, and then from that Python code, it lazily and locally generates a G code. So it's manufacturing as well. So it cuts down. You're not giving this huge pile of G code to something. You can give it an algorithm and it calculates. It's smart geometry. It adapts to the machine you're on if you need to. So let's say you want to output voxels, and on this machine the voxel resolution's here, but on this machine the voxel resolution's a little bit higher. You don't have to give it different voxel files. You can give it the same program, and it will return the voxels for the resolution you need. So all the power of code, which is awesome. There's some bad things, but I'm out of time, so no. I'll mention the bad things too. Endless loops, right? You don't want to put your 3MF file in a machine and have it lock up the machine, right? So you have to deal with things, all the problems with code. Bad actors. This is the one that I hate these folks, because now you need to have security in there. So you don't want to put in a file in your 3D printer and suddenly your 3D printer spying on everything you do. That wouldn't be so good. Lots of solutions. So these are things. If you're on Discord, next year I want people's Discord IDs on their badge too. We're talking about other things. So there's sandboxing and there's WebAssembly and other things that are really, really good. Code reps, I meant to give a shout out to for the NTOP folks there that were talking about this. A lot of this came from some common origins with the DARPA project, so code reps maybe is an interesting one as well. And finally, I'll get off the stage. So contact, if you want to connect with me, like I said, we're always interested in working with you all. In supporting the community, in doing different things. Again, I'm on the technology side, so I'm not really, I can be friends with everybody, right? So Siemens is hard sometimes because one company will be a competitor, one business unit, but another business unit's a partner, and another business unit's a customer. In my case, so I get to be, like I said, friends with everybody. So thank you. Thank you very much.